We're now going to look at the quotient rule. The quotient rule is the opposite rule to the product rule, where in the product rule we're looking at differentiating a function which was the multiplication of two different functions. The quotient rule we're looking at differentiating functions which is the division of two different functions. And we're going to look at two different cases, one where you don't really need it and one where you have to use it. In the first case, we can actually split up the numerator to make this y equals 3x squared over x minus x over x, which is 3x minus 1. If we then differentiate that, we simply get 3. Pretty straightforward, no special rules used. However, for the other example, x over 3x squared minus x, because there's only one thing on the numerator, we can't split this up. Now, one option is to take the whole denominator to the power 1 and rewrite this as x times 3x squared minus x to the power negative 1. And then we could use the product rule. However, there is also something called the quotient rule, which allows you to differentiate quotients without having to rewrite them as a product. So, the quotient rule. If you have a function that is in the form u over v, where both u and v are functions of x, then the quotient rule says that dy dx is equal to u dash v minus uv dash. So far, it's almost identical to the product rule, except that there's a minus sign instead of a plus sign. And that's all divided by v squared. Proof for this rule will be at the end of this video. So, looking at differentiating that function again, u is always the numerator, so u equals x, which means that u dash is 1, and v is the denominator, 3x squared minus x. So v dash is 6x minus 1. That means that dy dx is equal to u dash times v, so 1 times 3x squared minus x, minus u times v dash, x times 6x minus 1, all over v squared, 3x squared minus x to the power 2. Now, there aren't many cases where you would want to expand the denominator, so let's just leave it as it is. But we can expand and simplify the numerator. It gives us 3x squared minus x, minus 6x squared plus x, all over 3x squared minus x, all to the power 2, which in this example gives us negative 3x squared. The 2 negative x and plus x will cancel, all over 3x squared minus x to the power 2. And that is as far as we can simplify this function. You might get asked, find the gradient of the curve y equals x minus 2 all over the square root of x plus 3 at x equals negative 2. Now we should know that the word gradient means just find dy dx when x equals negative 2, i.e. differentiate and make x equal negative 2. So, u is the numerator, x minus 2, which means u dash is 1. V is the denominator. Now, when we're differentiating, it's best to rewrite this in brackets. So, x plus 3 to the power of a half. So, v dash, use the chain rule, bring the power in front, rewrite the bracket, reduce the power by 1, and times by the derivative of the bracket, which simplifies to make 1 over 2 and bring the negative power to the bottom of the fraction, which can be rewritten as a square root, 1 over 2 square root of x plus 3. Using the quotient rule now, dy dx equals u dash times v, so that's 1 times x plus 3 to the power of a half, minus u times v dash. When you times x minus 2 to v dash, the x minus 2 will just go to the top of the fraction, and 2 square root x plus 3 to the bottom, all over v squared. Now, since v is a square root function, when you square it, you just get rid of the square root and you're left with x plus 3. Now, simplifying this slightly, it is possible to simplify this a lot more than I'm currently doing. But because I'm just going to substitute x equals negative 2, it's probably better just to sub x equals negative 2 and work it out than risk making a mistake. However, after this, I will show you how to simplify this. So at x equals negative 2, dy dx equals square root of negative 2 plus 3 minus negative 2 minus 2 all over 2 times negative 2 plus 3 all over negative 2 plus 3. Now it's worth noting that negative 2 plus 3 is just 1, so therefore we have the square root of 1, which is 1, minus negative 4 over 2 times the square root of 1, which is just 2 times 1, or just 2, all over 1. That is 1, and then negative negative makes a plus. 4 divided by 2 is 2. All divided by 1 doesn't matter. We get final answer of 3. Now, if you were wanting to simplify this, let's just copy that. To simplify, we need to firstly add the fraction on the numerator. To get a common denominator, let's times the denominator of the first one by 2 root x plus 3, and so also to the top 2 root x plus 3. That gets us now 2 times root x plus 3 times root x plus 3 is just 2 x plus 3, and then minus the other side, x minus 2, since it is now all over the same denominator, which is 2 square root of x plus 3, and that has all been divided by x plus 3. We can then simplify the numerator. This is 2x plus 6 minus x plus 2, all over 2 times the square root of x plus 3, all divided by x plus 3. When you divide a fraction by another number, that just goes to the bottom of the fraction. So it's really like doing square root of x plus 3 times x plus 3, which gives us x plus 8 all over 2 times. And now since these are the same, just one is x plus 3 and one is x plus 3 to the power of half, we can just add the powers, which is x plus 3 to the power of 3 halves. If you were to sub x equals negative 2, we should then get the same answer. In x equals negative 2, we get negative 2 plus 8 all over 2 times negative 2 plus 3 to the power of 3 over 2, which is 6 over 2. And it's been multiplied by 1 to the power of 3 halves, which is just times by 1, which means we get 3. I would say in an exam situation, unless it says to simplify, which doesn't really ever say for these sort of questions, it's better to just sub x equals negative 2 at the earliest possible moment than risk making a mistake with your simplification. Now, last example. In class, I showed that y equals tan x differentiates to sec squared x, and I didn't give any reason for that. So we know that this is dy dx equals sec squared x. We are now at a point that we can learn why this is. Another way of writing tan is sine x over cos x, which means that u is sine x and v is cos x. So u dash is cos x and v dash is negative sine x. And we showed graphically why sine differentiates to cos and cos differentiates to negative sine in class. That means that dy dx is u dash times v, so cos x times cos x, minus u times v dash, sine x times negative sine x, all over v squared or cos x squared. Now simplifying the numerator, we get cos squared x plus sine squared x all over cos squared x on the denominator. Cos squared x plus sine squared x is equal to 1. That was one of the first identities that we learnt in the trig unit. All over cos squared x. Now since 1 over cos is equal to sec, 1 over cos squared is equal to sec squared, which is the answer that we expected. I'm now going to show the proofs for the quotient rule using two methods. One is going to be using the product rule, and another is using differentiation from first principles. Using the product rule, if we have y equals a function of x over a function of g, that means that this is also the same as a function of x times the inverse of g by bringing it to the top of the fraction, which is a product. So that means that u is fx, so u dash is f dash x, v is gx to the power negative 1, so v dash is you bring the power in front, you rewrite the bracket, you reduce the power by 1, and times by the derivative of the bracket, g dash x, which simplifies to negative g dash x all over gx to the power 2. Similarly, v can simplify to 1 over gx. So we can use the product rule now. dy dx is u dash v, so that is f dash x over gx plus u times v dash. So that is fx times negative g dash x over gx all to the power 2, which gives us f dash x over gx. Now it's a minus fx times g dash x over gx all to the power 2. In order to add these two fractions, in order to subtract these two fractions, I need to times the bottom by gx of the first fraction and the top by gx. That gives us f dash x gx minus fx g dash x all over gx all to the power 2, which if you treat, instead of fx and gx, we treat it as u and v, we get u would differentiate to u dash, v minus u times v dash all over v squared, which is the quotient rule. The second proof is a little bit more rigorous, doesn't use the product rule, it's just using first principles. Same start, and I'll just write the first principles rule above, which is that dy dx is the limit as h approaches 0 of function of x plus h minus function of x all over h. So, in this case, dy dx is equal to function of x plus h over function of g of x plus h minus function of x over function of g all over h. Now I see fractions So I'm going to subtract these two fractions on the numerator. So that gives us function of x plus h gx minus function of x times g x plus h all over g x plus h times gx. And when I divide by h to this, that's just like putting h on the bottom of this fraction here. Just going to duplicate that so we've got it lower. Now, in terms of our numerator, I want something that gives me something that resembles this, because that's what we did with the product rule. And I see function of x plus h times gx, but I don't see a function of x times gx. So I really want fx plus h minus fx. So what I can do is I can just subtract function of x times gx. If I subtract something, I also have to add it, so that I've effectively just done adding 0. Then I'm going to factorize, at least at the beginning, these two terms here, giving us f of x plus h minus f of x times by gx. And if I factorize the other two, this one and this one, I get minus function of x is common, g of x plus h. And since I've done a minus outside here, but the second term is actually a plus, I then need to make that a minus, g of x all over h times g x plus h times gx. Of course, we shouldn't be forgetting our limit as h approaches 0 to everything. Now, we can split this up into its two numerator parts. We get the limit as h approaches 0, function of x plus h minus function of x all over h times g of x all over g x plus h times gx minus g x plus h minus gx all over h times function of x all over g x plus h times gx. Now when I make the limit go to 0, well, this here is just a definition of f dash x, and this here is a definition of g dash x. So we get f dash x times gx over, now h is 0, we've just got gx times gx minus, now this second one becomes g dash x times fx all over, and again g of x plus h becomes just gx times gx. Simplifying, we get f dash x times gx all over gx to the power 2 minus f of x times g dash x all over gx to the power 2, which gives us our quotient rule, which is f dash x gx minus f of x g dash x all over gx squared, which if we change f to u and g to v, then then we have u dash v minus u v dash all over v squared, which is our quotient rule.